Chapter 3 is now where we combine what we've done in the last chapter and adding a new twist to it to give it a new name. In Chapter 2, we first discussed the difference quotient. What was the difference quotient? Yeah, that's different. Yeah. So it's the f of x plus h minus f of x all over h. And then the limits of functions as x approaches some number. So that's what we're doing here. So what we're doing here as h goes to 0. If we put those two together, we now define what this first half of the course is about. That will lead us to defining what we call a derivative. So, looking at all this stuff, what exactly do you think a derivative really is? So what is a derivative? Any guesses? With what we discussed here. What did these discuss? What about a certain point? So what did the difference quotient tell us? What was that looking for? Slope of what? Well, originally, yeah. We started off with the slope of the secant line. Through 2 points. X1 to X2. We call this area H. As H went to 0, we now found the slope of the line tangent to the function at a single point. And that slope of the line tangent to the curve is what this really told us. And then we're slowly. So what's the other names for slopes? Slopes of lines. Is that the only thing we deal with? good. What kind of rate of change? Well, let's say general right now. And the rate of change versus the slope, it all depends on what you're looking for, what you're given. Because the rate of change could be the change of the position of an object to its velocity, the speed, the velocity, the acceleration, and jerk. We can look at biological life forms, how they grow or decay in growth. We can look at, well, our first two examples we looked at was what? Gravity, an object falling. Then we looked at two things specifically with that gravity example, that rock falling. What were the two things? Okay, and then with a specific time. What are those called? What's the difference between those two? Average versus instantaneous rate of change. Remember how hard it was to find instantaneous rate of change? Because we had to find two objects and then make one point get closer and try to see a pattern with the slopes. Well, hopefully with this, we'll cover this chapter, that takes care of that. Let's look at an example. In your packet, it's example 1. A, find the slope of the curve y equals 1 over x at any point x equals a, where a does not equal 0. Bless you. What is the slope at x equals -1? So that's our first question. Here, find the slope of f of x. So how do we find the slope? Do we know any formulas for it? Or do we not just look at a formula for it about 8 seconds ago? We first have to look for this one. So in our example, we have the limit as h approaches 0. What's our equation going to look like? What's f of x plus h going to be? What's our f of x? 1 over x. So what's the first part going to be? 1 over x plus h. Minus f of x is for x. But it's saying here now x equals a. So what we have now is this. The limit as h approaches 0 of 1 over a plus h minus 1 over a over h. So how do we fix this? What do we have to do? We haven't simplified this stuff yet. We can't plug in because the only h we know is 0. That's undefined now. So what do we do algebraically? What do we do on top? How do you subtract 1 over a plus h minus 1 over a? Not yet. No, we wouldn't in this case. The complex conjugate would be done if we have imaginaries or if we had radicals with negatives in them. Let's simplify the top. How do we simplify the top? Rationalize the denominator of the numerator, right? So this is a plus h. This is a. So what do we need to make them equal? We get the denominators the same. So what does the first one need to have a common denominator? It just needs an a. Because this one has an a, this one doesn't. This one has an a plus h, which is not the same thing. So we need an a over a times 1 over a plus h minus 1 over a. What does the right side need? A plus h. Be very careful. A plus h and a are not the same. I can't just add an h to it because it's a different function. So my common denominator on the numerator is a plus h, which makes it a times 1 is a minus a plus h over h. Let's simplify the numerator. I distribute that negative sign in there, so it's a minus h. The a's cancel, so we have negative h. Take the top fraction, leave it alone. And the bottom is a fraction, so we flip it. The h's cancel. We have a negative 1 on top. A plus h. H goes to 0, so we're left with negative 1 over a squared. What does that represent? What does that represent? What is that? What is that? The slope of the line tangent to the curve at any a I give you. So what it said was, now let's try when x is -1. So when a is equal to -1. What do we get? So we know that our slope is -1 over a squared. So when x is equal to -1, yes, our slope is 1. B. What B is asking for is, where does the slope equal -1/4?
It being -1, wouldn't it being a squared?
Oh, the squared. Yes, I forgot to square it. So it becomes -1. Yes, I forgot to square. I was looking at the next one. Where does the slope equal -1/4? So what's the slope? So it's the slope is equal to -1/4. So what are we solving for? We can reciprocate those. So we have a squared equals 4. Since they're both negative, I don't need negatives. They're both 1 on top. So the only way they could be equal is if the denominators are equal. How do I solve for that? What is it equal? So my answer is ±2, because we have to have 2 solutions. So is that my answer? What's the question asking for? Where? Where indicates a location. So what is the location of our answer?
X coordinate would be 2, and the y coordinate would be 1/2.
Yep.
The other one.
Because remember, our formula said the curve at y equals 1/x, or 1/a. So when a equals 2, a equals -2, y equals 1/2, y equals -1/2. So it's at 2, 1/2, -2, -1/2. Because where is a location? A location is a point. A point is an ordered pair. And the last question says, what happens to the tangent line to the curve at the point at this point? as A changes, what happens? What's the graph going to look like? What's the graph of our function 1 over x? In which quadrants? This is quadrant 1. This is quadrant 2, 3, and 4. 1 and 3, right? So we know by looking at those graphs, what do we know about the function itself, the graph of the function? One over A is always decreasing. As x goes from left to right, no matter which side you're on, it's always going to be decreasing function. So since it's decreasing, what do we know about the slope? The slope is always negative. As A approaches 0, the slope approaches what? Is it a positive infinity or is it negative infinity? Because it's always, the slope itself is a negative slope. So it's always, since it goes all the way down there, it's going to be a vertical line, which is an infinite slope. As A goes to infinity, the slope goes to 0. Because as it goes this way, the slope becomes more and more and more dampened and becomes very close to a horizontal line. So that's what happens. So as it goes to infinity, as A goes to infinity, it becomes more horizontal. So far, so good? So let's look at, since we've discussed derivatives and we've defined them as the limit of that, this is how we first define a derivative. That little symbol there defines a derivative. It's the derivative of a function at a point x. So make it x sub 0. So it's a specific point. So it's at that specific location. So this could represent the slope of the secant line. So what? 2 this could be the average rate of change of a function and the derivative can give us the instantaneous rate of change. With respect to x. At the point x of 0. So it could be the slope of the secant line giving us, I forgot to finish that one, the slope of the line tangent. At point x sub 0. I forgot to do the last part. So you see what the derivative does. Think of how much work we have to do to find the instantaneous rate of change in chapter 2. Now it does it in one step. Example 2. This is the rock falling. And we have y equals 16t squared. So it says the rock fell at 16 feet, 16t squared feet during the first t seconds. And the average rate of change over increasingly shorter intervals. What was the rock exact speed at t equals 1? So how would you find that? We're looking, what this question is asking for average or instantaneous rate of change. it's at t equals 1, that sounds pretty instantaneous. So this is an instantaneous rate of change. So that means it's looking for what? It wants the derivative of this function. So whenever it wants instantaneous rate of change, and it gives us only one time, then we have to find the derivative of it. So we have the limit as h approaches 0 of 16 t plus h squared minus 16t squared over h. Algebra. Okay, remember, that's it for calculus. That calculus has told us what to do. How do we solve the rest of this? Algebra. So what do we have to do first? We have to do t plus h squared. So we have 16 t squared plus 2 th plus h squared minus 16 t squared all over h. The limit as h goes to 0. Okay. Distribute 16 t squared plus 32 th plus 16 h squared minus 16 t squared over h. The 16 t squares cancel. (32 th plus 16 h squared over h). So on the top, what can we factor out? (32t plus 16h all over h). The h's cancel. H goes to 0. So it's asking us, what is the instantaneous rate when t equals 1? Feet per second. What do you think? First, all it is doing now is now we're just giving, we've been doing this all along in chapter 2. We've just now given it a name. Okay, then that's it for that section. Glad you're online. So, not a problem. All right, let's finish. That's it for that one.